So we want to look and just do a quick recap on some of the sorting algorithms. We looked at, and I asked you to look at three of them: selection sort, insertion sort, and merge sort. We're going to come back to searching here in a second, but let's focus first on the sorting algorithms. As I said in our post the other day, there are a couple of things the AP would expect you to know about this. Number one, you don't necessarily have to code these algorithms in this class, maybe in the future, but not right now. What I would like you to understand is, first, what is the general strategy for these sorts? Kind of what, if we were to walk through them, what are the mechanics of the sort? Number two, to know a little bit about the sort, as far as when it is efficient, when it's not efficient, what is it good for, what is it not good for. So we really want to look a little bit more about these sorting algorithms, not necessarily how they work with code. Coding it would maybe be a different class in the future. You may take that in college. Let's take a look first at the selection sort. The selection sort is a little interesting. So the arrow is always going to point at the element that we're trying to figure out which value in the array belongs in that position, right? So we're trying to identify what value in the array belongs in index 0. Okay. So we are always going to try to, anytime we go through the array here, we're always looking for what is the smallest known value that's left in the array that has to be sorted. Because we haven't done anything yet, we can assume that the smallest value is currently sitting in index 0, and its value is 7, because we haven't looked at anything else yet. And now we're going to go element by element. We're going to go element by element and try to see, is there anything else smaller than the 7? Great. So on the next, is the 6 smaller than the 7? Yes, it is. So now the smallest known value is 6, and the index of the smallest value is 1. Great. And we're going to keep going. Is the 11 smaller than the 6? No, it's not. Is the 17 smaller than the 6? No, it's not. Is the 3 smaller than the 6? Yes, it is. The 3 is now the smallest known value, and it's currently sitting here at position 4. Is the 15 smaller than the 3? No, it's not. Is the 5 smaller than the 3? No, it's not. 19, 34. No. All right. So we now know that the smallest known value in the array is 3. We want the 3 to show up here in position 0. So what's going to happen is we're now going to swap the values. Right? The 3 now moves to position 0, and 7 moves here to position 4. We will now consider the 3 to be in its proper spot in the array. It has been efficiently sorted at this point. Okay. Next is we want to figure out what belongs in position 1. Okay. We'll assume that the 6 belongs there until we're proven otherwise. Is the 11 smaller than the 6? No, it's not. Is the 17 smaller than the 6? No, it's not. 7, 15. The 5 is smaller than the 6, so now the 5 is the smallest known value, and it's sitting at position 6 currently. The 19, the 30, and the 14, no. So the 5 is now the smallest value. It belongs in position 1, so let's swap them. Great. The 3 and the 5 are now considered to be in their proper position. So now we have to fill position 2. You follow the pattern now. Okay. The 11 is 17 smaller. Is the 7 smaller? Yes, it is. So now that's the smallest value. We're holding on to its position. Is 15 smaller? Is 6 smaller? Yes, it is. So the 6 is now the smallest known value. 19, 30, 14, no. So the 6 is currently sitting at index 6. So we want to swap 6 and 11. Okay? 3, 5, and 6 are now in their proper position. And now I think we're going to just continue to sort. So if you're kind of following the pattern here, the 7 belongs there. The 11 would be the next element that belongs there. So we're going to swap the 11 and the 17. The 14 and the 15 will swap. Now we're looking at position 6. The 15 and the 17 have to swap. We're now looking here at position 7. The 17 belongs there. And in position 8, the 19 belongs. Okay? So those are basically the mechanics of the selection sort. The way I will describe the selection sort, the best way I could describe it, is what we call a search and swap algorithm. This is the only algorithm we're going to look at that has this swapping pattern in it. Okay? So one of the questions they often like to ask is, let's say, how many passes of the array? How many times do we have to go through the entire array in order to get it finally sorted? And the answer here is, for the selection sort, is for an array of n elements, whatever the n equals, the array gets sorted after we do n minus 1 passes. Right? So we had, if I back up for a second, we had 10 elements in the array, and we had to pass through this array 9 times in order to get it all sorted. Right? So the number of elements, it's always n minus 1, is the number of times it would take to sort the array. Okay. After the kth pass, after the second pass, the first 2 elements are in their final sorted position. After the 5th pass through, the first 5 elements are in their final position. Okay. Selection sort is not very efficient. For a very large number, it's not efficient for a couple of reasons. First, it's for the n minus 1 passes. Secondly, the other thing we care about is the number of comparisons that have to happen. If I back up here for a second, I'm going to put all of these back. Okay. I look at the number of comparisons that have to happen. We have to, in order to figure out that the 7 is the smallest, we have to compare. Watch the number of comparisons. 1, 2, 3, 4, 5, 6. We have to compare that against 6 other numbers. And if we really look at it, we can start to count the number of comparisons that have to happen. So for that reason, selection sort is considered to be not so great. It's not the most efficient array that we can sorting algorithm that we can use in an array, but it is one method. Okay. So again, we always want to focus on, what does the algorithm do? What are the mechanics of the algorithm? How efficient is it? Right. And a little bit about how many times does it take to be able to sort the array? How many passes through the array does it take to sort it? Okay. Selection sort, that's the find it and swap it algorithm. Next is called the insertion sort. We are basically going to divide this list into a sorted portion and an unsorted portion. So right now, I'm going to say that anything that's highlighted in orange is currently sorted, and anything that's in light pink is going to be not sorted. So right now, let's assume that the 7 is in its proper position. Okay. We're now going to go to the next element in the array and figure out, if I were to take this and just take it and put it in its own position, where does it belong? So if I were to take the 6 and put it into the sorted position, it would really belong before the 7, right? So we want to compare it against where it belongs in the sorted section and keep going until it's in its right spot. Okay, so watch how this would work. So now we took the 6 and dropped it before the 7. Great. So now this half is sorted. Now the 11. Where would the 11 belong in this range? Well, the 11 is kind of already in its spot because it would belong to the right of 7. So we're considered that to be sorted. And in this case, the same for 17. When we get to the 3, what we really start to ask ourselves is, well, does the 3 belong to the left of 17? Does it belong here? No. Does it belong here? No. Does it belong here? No. Does it belong here? Yes, it does. So the 3 would go in the front. Where does the 15 belong now? Does the 15 go before the 17? Maybe. Yep, it belongs between 11 and 17. So we're just going to drop it in there, right? So the 15 would belong in there. The 5 would get dropped over here. Then, right, you follow? So we're basically going to look at the sorted elements of the array, the sorted part of the array, and then go to the next thing that has not been sorted, pick it up, and just put it where it belongs. So ultimately, you get an array that looks like this. Okay. So this is the insertion sort. We're just going to take the items out of the array and insert them where they belong. Okay. Same deal. For an array of n elements, the array is sorted after n minus 1 passes. We still have to go through the entire array to make sure we found the right values. Okay. After the kth pass, after the x number of passes we go through, it's really the sorted portion of the array are sorted in relation to each other, but not maybe in their final indexes, right? So when we went through there 3 times, the first 3 elements were in the right order compared to each other, but there might be other changes that are going to come later on. Okay. Sometimes they also ask about the worst case scenario and the best case scenario for these sorts. The worst case scenario for the insertion sort is that the array is sorted in reverse order, where everything is backwards, and now you have the maximum possible number of comparisons that have to be made and the maximum number of moves that have to be made. The best case scenario is that the array really already comes in its own order. It comes in the proper order, right? Each pass through the array only really is one comparison, and there are no moves to be made. Right? So the best case scenario is that the array is already sorted, and then at that point, it wouldn't take very long to figure that out. In general, we do say that the insertion sort is it's not that efficient. Again, think about it. The number of passes through the array that have to happen, the number of individual comparisons that have to happen. So again, maybe not the most efficient way of doing it when you have a larger array to sort. Okay, so again, the insertion sort is take the element and insert it into its right spot in the sorted element, in the sorted section of the array. Okay. The next one can be a little bit confusing. It's called a merge sort. Okay. The general theory behind the merge sort is we're going to call this a divide and conquer strategy. We are going to break the array apart and then slowly start to bring it back together. Okay. So the first thing we're going to do is if this is the array that we're working with, we're going to break the array into 2 sections. Right, so we can probably figure out the length of the array, divide by 2, that's the midpoint of the array, and then we'll split everything from the beginning of the array to the midpoint, and then the midpoint to the end of the array. Something like that, right, if we were coding this. So after like the first pass of this, there's probably some loop involved in this. After the first pass of this loop, we would have broken this array down into 2 separate arrays. And then we're going to take each of these, really this is array 1 and array 2, we're going to break those down into smaller parts. So we'll take this array and split it in half. So here's 1 array, 2 arrays, 3 arrays, and a 4th array here. And then we're going to keep breaking it down until we really get every element in this array in its own 1 element array. So we'll break the 3827 into their own elements, et cetera, right? So we basically keep dividing the array until all the elements are separate. And then we're going to start to merge them back together. But when we put them all back together, we want to be able to put them in their proper order, really in respect to each other. Okay, so if I were to start here, maybe we're going to take these and we're going to start to group them in by 2s. Okay, so I want to take a look at these elements and decide in this grouping, are they in the proper order? No, they're not. So I will put them in the proper order to make this become 2738. This gets put in the proper order, 343. The 9 and the 82, they are in their proper order, so they'll just get brought together. And the 10 is by itself, so we'll leave it alone. And then we want to merge these elements together. So it's almost like you actually start from the left side of each one of these, and we're going to just compare the two, the 27 and the 3. Which one belongs first? We'll take the 3. The 27 and the 43, which one belongs? We'll take the 27. The 38 and the 43, which one belongs? We'll do the 38 and then the 43. Here we'll take the first element in each one of these arrays, the 9 and the 10. Which one belongs first? We'll take the 9. And then we'll compare, is the 10 or the 82 next? The 10 would be next. And then we'll take the 82. All right, so now we've merged these arrays together. And now we have to merge these together. So again, we'll start from the left-hand side of each one of these. The 3 and the 9, which one has to come first? We'll take the 3. The 9 and the 27, which one comes next? We'll take the 9. The 27 and the 10, which one do we need? We need the 10. The 27 and the 82, which one do we need? The 27. The 38 and the 82, which one do we need? The 38. 43 and 82, we'll take the 43, and then the 82. Okay, so we basically have taken this one array, we broke it into its individual elements, and then slowly started to put it back together in its right order. Okay, we're going to break and we're going to merge it back together. That's why they call it a merge sort. Okay, this is what we call a divide and conquer algorithm. This is really important. Anytime they talk about a divide and conquer algorithm, divide and conquer algorithms are always more efficient than any other algorithm. Okay, this is what we call a recursive sorting algorithm. If you remember, we talked about recursion, which in the 2020 class, we haven't talked about it yet. Recursion is when a method calls itself over and over and over. A method calls itself. If you think about it, we keep doing the same thing over and over. When it came to break down the array, we broke. And then when it came to put it back together, we kept doing the same merging and comparing over and over and over. So it really does the same two very specific parts, the splitting and the merging. It does them over and over. So it's called a recursive algorithm. Divide and conquer sorts can be very efficient. First, because if we think about this, right? When I had to figure out where was the proper position for the 38, I didn't have to compare 38 against every other element in the array. I only had to compare it against the item that was next to it. So I think the number of comparisons that happen to figure out where they belong is a lot smaller. So this can actually be a lot more efficient. Anytime I don't have to touch the entire array, but I can touch a smaller subset of the array, that will increase efficiency, if that makes sense. Unfortunately, the code for this is very complicated. The code for the selection sort is a lot simpler. The merge sort gets a lot more complicated, and the code is much longer. It also requires a bunch of temporary arrays to be able to hold all these values. So it could maybe not be the most efficient way as far as memory usage is concerned, but as far as speed and the number of comparisons, the merge sort actually could be faster. Okay. If I had to summarize this and we had to put them together, the two things I want you to pay attention to. First is, what is the strategy being used? What is the technique being used? The selection sort is the search and swap algorithm. Find the next item and swap it around. The insertion sort is take the value from where it needs to go and put it into the sorted section of the array in its right spot. And the merge sort is the break it apart and then slowly merge it back together. Okay. When it comes to efficiency, the selection and insertion sorts are okay, but the merge sort is the fastest out of all of them.